And welcome to Module 1 of the Versa Essentials training. In this module, we'll review the WAN, or Wide Area Network. We'll look at how the WAN has evolved over the last 5 decades and key problem areas that network administrators face. We'll also look at overlay and underlay networks and describe the differences. Overlay network architectures are the fundamental technology of next-generation software-defined WAN designs. We'll also look at how security is implemented in today's WAN designs. To start, we'll look at the Wide Area Network, or WAN. The WAN is a network system that connects 2 or more distributed networks together. The service provider owns the WAN network and provides access to it as a service to the customer. Let's take a look at a customer deployment scenario. At a customer location, the WAN links are terminated on a customer premise equipment or CPE device. The link that connects to the service provider network is called the last mile through the service provider's point of presence, or POP. A POP is the nearest node from where a service provider will extend connectivity to a customer. Next, we'll look into the evolution of WAN technologies. Evolution of WAN technologies. The first generation WAN links used to connect distributed networks were deployed back in 1970 using X.25 virtual circuits. This was a simple packet-switched infrastructure used to connect offices and was often referred to as the first cloud service in widespread use. X.25 was replaced by SONET, or Synchronous Optical Networks, or SDH, Synchronous Digital Hierarchy Protocols. These were developed to transfer multiple data streams synchronously over optical networks using lasers. The minimum digital signal, or DS0, could support 56 kilobits per second. A DS1 or T1 line could support 1.544 megabits, and a DS3 or T3 line could support 44.736 megabits per second. These were point-to-point links that connected 2 locations. This was a dedicated infrastructure for connecting customers, and it was very expensive. Even today, large service providers use these technologies to deploy optical fiber networks in their core, although multi-gigabit Ethernet has become increasingly popular. Later, in the beginning of 1990, frame relay was introduced, which introduced the concept of pooled bandwidth. Service providers were able to utilize multiple T1 or T3 links and share the bandwidth among multiple customers while maintaining the integrity of the WAN link. This resulted in a lower cost of ownership, a simplified infrastructure, and better performance compared to X.25 based designs. It was deployed widely in enterprise networks and was a very popular option. In late 1990, MPLS technology was introduced, which was primarily designed to address challenges of slow packet forwarding. It functions by placing a tag on each packet, and devices in the network forward traffic based on the tag, or MPLS label, instead of an IP route lookup. When routers and switches became faster, the need for doing tag switching for speed was replaced by its ability to hide the IP payload within a tagged tunnel, and applications like MPLS-based Layer 3 VPNs, Layer 2 VPNs, and so forth became very popular. It proved to be a win-win story for both service providers and customers. It's fast, secure, and economical compared to the other solutions, and is very feature-rich. Service providers can use the same infrastructure to provide various flavors of service to customers and expand their operations. By far, this has been the most successful, widely deployed and accepted technology in different areas all across the globe. And its applications have helped enterprises build regional and global WANs. The next phase in WAN evolution was towards hybrid WAN and software-defined WAN. This was more focused on automation and agility to simplify WAN operations and management. Hybrid WAN empowers enterprises and allows them to make optimal use of their WAN resources. It provides feature-rich, intelligent traffic steering and traffic conditioning to enhance the end-user experience. Before we discuss software-defined WAN, it's worth spending some time to understand overlay networks and underlay networks. An overlay network is a logical connection between two devices, and in a WAN environment, these devices can be very far apart. The overlay network is transparent to the physical network that connects the two sites. The physical network enables the overlay network to be built by providing a transport path. The overlay network is a system of virtual wires that runs over the physical infrastructure by using tunneling technology. The customer traffic is encapsulated using a tunnel header and transported to the destination. The service provider transit devices don't have visibility into the end user traffic because the traffic is encapsulated. The end customer is in complete control of how and what they are sending through these overlay tunnels or virtual network links. Overlay networks have been used for a very long time. You may have implemented an overlay network without even realizing it. GRE tunnels and IPsec-based tunnels are examples of overlay network connections. They're a virtual network link that extends across a physical transport network. MPLS and MPLS-enabled applications use labels to create virtual network links. These virtual network links, or tunnels, are used to forward traffic between service provider edge devices in order to offer different levels of services. More frequently, VXLAN has emerged as one of the most versatile encapsulation techniques and provides a lot of customization. VXLAN was originally developed to transport Ethernet frames, but VXLAN GPE, or Generic Protocol Extension, has been widely used to encapsulate various kinds of protocols as it allows the VXLAN header to identify and encapsulate other types of traffic than just Ethernet frames. The underlay network is the transport infrastructure that a service provider provides as a service. The service providers build a network infrastructure to carry multiple gigabytes of traffic and provide different services to end customers, services such as leased line services, MPLS-based Layer 3 VPN, and so forth. The core infrastructure is shared among multiple customers and various types of services are offered. With the evolution of MPLS and MPLS-based services, service providers also provide service level agreement or SLA-based services to enhance end-user experience. When an SLA is in place, the service provider guarantees under contract to provide a circuit with predefined performance guarantees. The control plane. In a network architecture, a system is put in place to provide instructions on how the devices should perform their tasks. It analyzes paths, chooses which path is best, maintains critical functions, and distributes routing information throughout the domain. This is based on the configuration of each device. With software-defined networking, the calculations and decision-making processes are centralized so that individual devices in the network give up some or all of their control over routing decisions and the decision-making processes. In a software-defined WAN environment, a central node or set of nodes are responsible for sharing details about the network topology to devices in the network to enable traffic flow. This central node is also called a control plane manager. Every networking node will talk to this central control node, and the system of communication and information sharing is called the control plane. In many service provider MPLS-based VPN deployments, route reflectors act as a centralized point for routing information. They share reachability information with provider edge devices about a customer's VPN topology, LAN subnets, sites, and so forth. The data plane refers to the actual transit traffic forwarding processes within the network. Where the control plane informs devices about how to reach destinations, the data plane does the actual work of processing an incoming packet, comparing it to a local routing or forwarding table, and choosing the next hop interface. Our next topic is security in today's WAN. In current MPLS-based VPN solutions, individual customer traffic is isolated by the virtue of encapsulation using MPLS labels. The service provider provides a private connection between customer sites. But private does not necessarily mean secure. Although packets are separated by using MPLS labels, there's no encapsulation applied to transit devices. Service providers usually don't provide any firewall or security services. Their job is to connect your sites, not secure your data. When a WAN provider does provide security services, it's based on their offerings, and it limits what you are able to implement. And it also limits your control over those security features. Service provider security becomes even more complex when the service provider for one area doesn't provide service in another area, and different service providers are needed to connect remote sites. If secure data transfer is needed between sites, it's up to the customer to encrypt the traffic before it is placed on the service provider circuit. Next, we focus on some of the challenges faced by network administrators. One of the biggest challenges at the branch level is the complexity in managing and monitoring today's networking services, especially when various network services are delivered through different vendors. With difficulties in managing traffic across a complex environment, users often have a poor experience, such as slow application performance or poor video and voice calls. This complexity directly impacts agility at the network layer. Provisioning and onboarding procedures are complicated and need local assistance at the branch level, which results in longer deployment timelines when new sites need to be added to the infrastructure, or when existing sites require updated equipment or services. Additionally, private MPLS VPN services can be expensive. As a company grows and new sites are added to the existing infrastructure, those costs can add up quickly. And then, even after paying premiums for MPLS-based WAN links, outages can still occur. Another challenge is providing internet or public network access. Service provider links are circuits between sites and locations and don't natively provide an internet connection. For internet connectivity, customers need to provide a public circuit. This can be centralized at a corporate site or distributed at each location. If access is provided at each location, it requires the addition of routing and security devices for each connection and the management resources to configure, deploy, and manage those devices. If access is provided at a central location, such as a company headquarters, larger, more expensive equipment is needed to process the entire company's public traffic. In addition, since private and public data will have to cross the service provider links, connections to branches require more data throughput and become more expensive. This is the end of Module 1 of the Versa Essentials series. In this module, we looked at how WAN architectures and technologies have evolved, we described some of the challenges that companies face with current WAN technologies, we explored the fundamentals of overlay and underlay networks, and lastly, we looked at security implementation in today's WAN. Thank you for your participation in this module, and we hope you found the session informative.